Hey, good morning. So I'm having a lot of problems with my internet because of the wind storm that's going on, and so I'm just going to do my lecture today um, on this, and then you can watch it whenever you want to. So to start out with, we're talking about this electric charge and electric forces. Um, so we have these electric charges. So electric charges, all matter is made up of particles. We know that they're all made up of atoms. So here's a picture of an atom right here, and of course in atoms they have a couple of different particles. We've got positively charged protons. We have neutral neutrons, and then negatively charged electrons that zoom around on the outside there. So they're all in there, positive, negatives, and of course we have the two types of charges, charged particles. We have a positive particle and a negative particle. Those neutral objects, they have an equal pole either way. It doesn't really matter on those. But what we're looking at here is how these things repel or attract each other. So like charges are going to repel each other. So positives and positives repel each other, negatives and negatives repel each other, but opposite charges attract each other. They're going to come try and neutralize each other out. So when we have this unbalanced electrical charge, they call it a static charge. So if we have an object that has more negative than positive, or more positive than negative, then we can have a static charge on those objects. Okay, so we're talking about forces. Forces are things that are applied from one object to another. So how much force is applied when we're talking about electrical forces, how much force is applied is determined by two things. Number one is determined by how much charge is on both objects. So if you have a lot of charge, you'll have a lot of force. If you have not a lot of charge, you won't have a lot of force. And then the second thing is the distance between the objects. So the closer the objects are, the more force you'll have. The further apart they are, the less force you'll have. So if you think about when you're brushing your hair, especially for girls that have longer hair or boys that have longer hair, when you brush your hair, electrons are transferred from the brush. So we have negatively charged particles that are moving from the brush to your hair. The brush then is positively charged, and your hair is negatively charged, so they're going to attract. So if you take that brush and you bring it close to your hair, you'll see that your hair is attracted to that brush. But the further away you get from it, the less attraction that you have. Okay. All right, so we transfer electrons lots of different ways. So you probably have seen these kinds of things like insulators and conductors. If you've ever looked at a electrical cord, they have plastic around the outside and metal on the inside. And they do that because the plastic is an insulator. Insulators are material in which electrons cannot easily move. And conductors are materials like the copper inside of the wires there. Conductor is a material in which electrons can easily move. So we have this material on the inside of the wire that conducts electrons very easily, and then on the outside we have the plastic that is a insulator, and the electrons don't move very easily through that. You can transfer electrons a couple of different ways. I've got a little video I'm going to show you here, but transfer by contact. So if you look at this balloon and this wool sweater, if we take this balloon and we rub it against this wool sweater, we're going to be transferring electrons from the wool sweater to the balloon. So they have to touch one another, but they can do it that way. And we also have this induction, transferring by induction. So here we have this this negative balloon here, and we put it up next to these two Coca-Cola cans that are next to each other. They're touching each other. If you put this negative charge up next to this Coca-Cola can here, all of the negative charges are going to be repelled to the other side, as far away as they can get. So they'll go from this Coca-Cola can into this Coca-Cola can, so there's negative charge over here. And the positives will transfer from this Coca-Cola can over to this Coca-Cola can because they want to get close to the negative. They are attracted to that. And then if you separate those two cans apart, lo and behold, this can is positively charged and that can is negatively charged. That's charging by induction. So polarized when an electron concentrates at one end of an object. So these cans, they become polarized when you put this negatively charged balloon next to it. The negatives go to one side, the positives go to the other side. That's polarized. Okay, got this video here to watch. I'm going to turn the volume up.
There are three ways that objects can acquire a net charge. What we see here is an example of charging by friction. Electrons are being transferred by friction when one material rubs against another. Because electrons are lost by one material and gained by the other, the objects now have opposite charges and attract. This is the same situation that occurs when you rub your feet across carpet and are shocked by contact with the doorknob. The shock you feel is electrons moving from your body to the doorknob. This is known as a discharge. After the discharge, your body is neutral again. Electrons can also be transferred from one material to another simply by touching. When a charged rod is placed in contact with a neutral object, some charge will transfer to the neutral object. This method of charging is called charging by contact. If the object is a good conductor, the charges will spread to all parts of its surface because the like charges repel each other. Charging by induction can be shown using two insulated metal spheres. Uncharged insulated metal spheres touching each other form a single non-charged conductor. When a negatively charged rod is held near one sphere, electrons in the metal are repelled by the rod. Excess negative charges move to the other sphere, leaving the first sphere with an excess positive charge. The charge on the spheres has been redistributed or induced. When the spheres are separated and the rod removed, the spheres are charged equally and oppositely. They have been charged by induction, which is the charging of an object without direct contact. Charge induction by grounding can be illustrated using a metal sphere hanging from a non-conducting string. A charge redistribution is induced by the presence of the charged rod. The net charge on the sphere is still zero. Touching the sphere removes electrons by contact, and the sphere is left positively charged. The positively charged sphere is attracted to a negative rod. When electrons move onto the sphere from the rod, it becomes negatively charged by contact. When we touch the metal surface with a finger, charges that repel each other have a conducting path to a practically infinite reservoir for electric charge, the ground. When we allow charges to move off or onto a conductor by touching it, we are grounding it. Charging by induction also occurs during thunderstorms. The negatively charged bottoms of clouds induce a positive charge on the surface of the earth below. Most lightning is an electrical discharge between oppositely charged parts of clouds. The kind of lightning we're most familiar with is the electrical discharge between clouds and oppositely charged ground below. If a rod is placed above a building and connected to the ground, the point of the rod collects electrons from the air. This prevents a buildup of positive charge by induction. The primary purpose of the lightning rod is to prevent a lightning discharge from occurring. If lightning does strike, it may be attracted to the rod and short-circuited to the ground, sparing the building. Charging by induction is not restricted to conductors. Charge polarization can occur in insulators that are near a charged object. When a charged rod is brought near an insulator, there are no free electrons to migrate throughout the insulating material. Instead, there is a rearrangement of the positions of charges within the atoms and molecules themselves. One side of the atom or molecule is induced to be slightly more positive or negative than the opposite side. The atom or molecule is said to be electrically polarized. When an external negative charge is brought closer from the left, the charges within a neutral atom or molecule rearrange. All the atoms or molecules near the surface of the insulator become electrically polarized. Rub an inflated balloon on a sweater and it becomes charged. Place the balloon against the wall and it sticks. The charge on the balloon induces an opposite surface charge on the wall. The charge on the balloon is slightly closer to the opposite induced charge than to the charge of the same sign. Many molecules, H2O for example, are electrically polarized in their normal states. The distribution of charges is not perfectly even. There's a little more negative charge on one side of the molecule than on the other. Such molecules are said to be electric dipoles. Thanks for stopping by. We'll see you next time.
Okay, so that's pretty much explaining all those things there. But anyway, electrical discharge here. We're talking about grounding. Grounding provides a safe path for electric charges to flow safely into the ground. So here you can see this electrical discharge, lightning coming down from the clouds down to the ground. Scientists, they don't fully understand what causes lightning. However, many scientists think that lightning is related to the electric charges that separate within storm clouds. There's lots of materials inside of storm clouds, like water and snow and ice, and as they move past each other from the winds and stuff, they're going to cause that induction and charging because of touching, all those kinds of different things. And then the clouds become electrically charged. They need to discharge. So anyway, okay. That's all for chapter 19.1. I'll try and put up another one for 19.2 so you can watch that one later on today too. So have a great day, and I'll see you later.